I am Ziaur Rahman, the student of Department of INS, Scott University of Science and Technology. It is my presentation for the course of Functional Analysis 1, course code 324, and the topic of my presentation is Uniform Boundedness Theorem. In this presentation, we will first see point-wise boundedness, definition of point-wise boundedness and uniform boundedness, and then we will go through the statement of Bayer category theorem, and this theorem is used in this uniform boundedness theorem. So our main concern of the presentation will be this uniform boundedness theorem. But for this, first we will now what is uniform boundedness, what is point-wise boundedness, and also this theorem is used in this uniform boundedness theorem. So we will first see these things. So let's see. So what is point-wise boundedness? A subset M of this bxy, that is set of bounded linear operators, is said to be point-wise boundedness. This M is said to be point-wise bounded if for each x belongs to this x, the set, this set, we define this set that for every x belongs to this x, tx, that is all the t's from this M, all the t belongs to this M when applied on this x, and all these x belongs to this x. So this set is bounded subset of y. This is bounded subset of y. Then this boundedness is said to be point-wise boundedness. And here the x and y are normed spaces. Now let's see what is uniform boundedness. A subset M of bxy is said to be uniformly bounded if this M is bounded subset of, it is a subset of this xy, but if this is a bounded subset of this xy, then we will say such M is said to be uniform bounded. Such a boundedness is said to be uniform boundedness. So what is the difference between uniform boundedness and point-wise boundedness? Here all the operator belong to this and all the t belong to this, and this is the subset of this, and when this is bounded in here, then we say such a set is uniform bounded, and point-wise boundedness. Then this M, when applied on the element of x, and so we will get some subset of y, and this subset of y is bounded in y, then such a boundedness is said to be point-wise boundedness. Now we will also use Bayer category theorem for complete metric spaces. This theorem says that if a metric space X is complete, then this X, the finite subset, union of finite subset of this X is then we can write this X as the union of finite subset of X and finite subset of X and this X, and sum of this AK now contains a non-empty open subset. This is, and here AK is closed as well. So we will use this theorem in the uniform boundedness theorem. So let's see what is the definition of uniform boundedness theorem. The statement of this theorem is, let Tn be a sequence of bounded linear operator Tn x to y. Here this x is the Banach space and this y is a normed space. So this theorem states that when we apply this Tn on all element of this x, and the norm of such operator will be bounded if this is bounded, as this belongs to y, because this belongs to some subset of y, because here we take t and some sequence of x, and when we apply all this sequence on all of x, then we get some sequence or some subset of y. Then actually this, if this is bounded, this is bounded is in y. So we, from the definition of pointwise boundedness, this is bounded in, this is now bounded in y, but this boundedness is said to be pointwise boundedness according to the definition of pointwise boundedness. And we let this cx, the bound of this is some real number, we let this is cx, and the sequence of the norms. Then this theorem claims that the sequence of the norms is bounded. This is the some sequence in this Tn is some sequence in this x. So this will be bounded in this of bounded linear operators. There's some sequence of bounded linear operators bxy. Then that means this is bounded. This means that there exists some real number for which this condition is satisfied. So let's see towards the proof. So for every k belong, we will let's define a k subset of x. This a k contains this a k, for every k belong to n, there are some subsets of x. So, and this a k contains all such x belongs to this x, then for which this condition is satisfied, and there must exist, this condition must be satisfied because it is from clear from definition of this x, from the statement of this theorem. So for every x belongs to x, there must exist some k belong to natural number for which this condition is satisfied. So we will have to show that this Tn is bounded. This Tn is bounded. So for this, in this we will use Bayer's category theorem, for which this ak, there is a subset of x, all subset of this is closed. So let's see how this is closed. So for closeness, we will take some element belong to the closure of this, and later we will prove this, that this element belong to the set itself. So let's suppose that this belongs to this closure of this. This is the closure of a k, which means that for every element belongs, which contains every element, such an element for which there exists some sequence in this ak which converge to this x. So according to this definition, there exists a sequence in ak, then this x converge, this sequence converge to this x. This means that for every fixed n, we have this, because this x, this sequence is now belonging to ak, and according to the definition of ak, this condition is satisfied because this is the definition of ak. Every element belong to ak will satisfy this condition. And now we will obtain that the Tn of x will also satisfy this condition. This will also satisfy this condition because Tn is continuous and norm, and it is continuous as well, and Tn is a norm. We know that the set of all bounded linear operator is a norm, and since norm is a continuous, from this section 2.2 refer to section 2.2. This in this section it's clear that the norm is continuous. That is, this is a continuous mapping from a norm space X into a R. And what continuity means? Continuity means that for let's X is a norm space and Y is a norm space, metric space, let X be a metric space and Y be a metric space, then a mapping from X to Y is said to be continuous at a point X naught belong to X if for every epsilon greater than 0 there exists a delta greater than 0 such that this condition is satisfied. That is, the distance between these 2 points is less than delta, then there exists some epsilon for which this is satisfied. According to this condition, this continuity, by definition of mapping or this continuity, we will say that now this means that the limit n tends to infinity of this thing will be equal to this thing. Limit n tends to infinity of this is equal to this. So when this is less than k, its limiting position will always be less than or equal to k. So this means that by the definition of a k, this x now belongs to a k. It is clear from the definition of a k. Now this x belongs to a k. So we take an element from a k closure, and now we will get this element belongs to a k. So this actually means that a k is closed. And now for every x belong to x, there exists some a k. Hence, we can write this x is a countably infinite subset, union of countably infinite subsets of a k, because we define a k to be such a subset of x for every k belong to natural number which contain such element of x for which there exists k. So which contains such an element for which there exists, which is less than, whose norm is less than this k. So there for every x belong to this x, there must exist some subset of x for which this x belong to this, according to definition of this. It actually means that for k equal to 1, all element of x, this contain all element of x for which the norm of Tn of x is less than or equal to 1, and similarly for k equal to 2, this contain all element of x for which k equal to for which the Tn of x will be less than or equal to 2, and similarly for all elements. So we can write this x is countably union of countably infinite subsets. Since x is complete metric space, since x is complete, we know from the definition, from the statement of theorem, uniform boundedness theorem, then all the properties of Bayer category theorem are now satisfied. So we can use this Bayer category theorem, and this Bayer category theorem states that there must exist some ak, which contains an open ball. This is an open ball which whose center at origin x naught and radius with r, and this must be contained in sum of ak. We will let sum this ak to be ak naught. Let's say this contains in this ak naught. Here we will see some consequences of an open ball which is used in this theorem, and the first consequences of this is that BR, that is the open ball of radius r and center at origin, can be written in this form, that is the radius r multiplied with this open ball centered origin and radius whose radius is 1. And now this BR, what is this BR? This is the open ball which is centered origin and whose radius is r. And similarly this B1 mean that there is a open ball whose center is origin and radius is r1, whose radius is 1. This denotes radius. So according to definition of this ball, we can say that all the element will belong to this ball if distance between this if the distance between center and this element is less than the radius of this ball, that is, if this is an open ball, then and this is the origin O and this is the radius R, then all such element, for example here is X, then all such element will be contained in this open ball whose radius is less than R, whose radius from origin is, whose distance from origin is less than this radius. So we know this can be applied, this definition can be applied to this metric space metric, and then we will also, or we can also write this as well. Let's say this x by r to be z, and from here it is clear x is equal to rz. Now if they now use this rz and this in the previous in this, then we will get rz and br is equal to rz, such that the norm of z will be less than 1, that is radius of open ball centered origin at radius 1. Then we can also write this thing as well, and from here it is clear that this is the element of open ball whose center is origin and radius is 1. So we can write this is equal to this, and this is by definition equal to b1. So we can say that this br is now equal to rb1. This r can be written as rb1. This consequence will be used in uniform boundedness theorem. And let's see the second consequence is that every bxr, that is every open ball centered at x and radius with r, can be written in this form as well. This is the ball with radius r centered at origin O0. Let this y belong to this open ball, then this y belong to this mean that when this is open ball centered at x with radius r, then it contains all such an element whose distance from this center is less than this radius. So this means that this y will satisfy this condition as well. That is, according to definition, we can say that the distance between these two will be less than r. And similarly, we can also write this as well. Let's say this is equal to z. Now let's say this is equal to z. So then we can say that y is equal to x plus z. From here, when this is equal to z, then y is equal to x plus z. Now this norm of z is less than r, mean that this z belong to br, because this br is the open ball centered at origin and radius r. This is according to the definition of this ball. This z now belong to this br, and this y can be written in this form as well. So for every element belong to this ball, we can define such a set for which every element belong to this br. Then this set, then this y belong to this set as well, and this mean that for y belong to bxr, this y also belong to br. This means that bxr is a subset of xbr. We take on y from bxr here. We take on y from bxr, and now we get y belongs to x plus br. Y belongs to x. It is x plus br. So now this bxr is a subset of x plus br. So and also this is if and only if we choose y belong to this, then we can write y to be equal to this, and so performing all these steps. So this means that this also implies in this way as well. So this actually means that this is also a subset of bxr. This is also a subset of br. So when a is a subset of b and b is a subset of a, this means that they are equal. Now let x belong to x, we choose an arbitrary element of x not 0. So we set z is equal to x naught plus gamma x. Now we can write according to the conditions of consequences of open ball. We can write when this is the center of open ball, because we choose an open ball from this ak naught. This is an open ball from this ak naught, center at this x naught with radius r. So according to now these consequences, the element of this can be written in the form of this, that is for which and this element belong to open ball. We can use except radius, we can use r element which is less than radius. So this gamma is less than radius, and this will belong, so all element less than radius will belongs to this open ball as well. Now you can consider this x is an open ball center at origin with radius 1 as well, because according to the consequences we can write this. And now this z minus x naught norm of this will be less than r, because when you shift this x naught to this side and then gamma equal to this and then apply a norm, then this must be equal to this must be less than or equal to this r. So this x z this means that this z belong to b naught. Also this z is written in the form of also from the consequences of open ball, this z is belonging to this open ball as well. So now by equation 4, and from the definition of ak naught, we can write this is it, this we can write from the definition of ak naught. And for all n also, for all n, that is for all n here, and also we can write this tn of x naught norm of this will be less than or equal to p naught, because this x naught also belong to p naught, because this x naught is the center of this b naught. So this x naught also belong to b naught, so we can write this as well, because when this belong to p naught, this means that this also belong to this. So according to the definition of this, we can write this is well. Now from 5, that is from here, when we can obtain x is equal to 1 over gamma z minus x naught as well. So this yields for all n, when we applied on the norm in the norm of this, then we get, because this is x is equal to this thing, and we can take out 1 over gamma as well, because it's a scalar multiple. And applying triangular inequality of norms, we can write this is equal to this, and now this norm of this is less than k naught, because here this is norm of this is less than k naught, and norm of this is less than k naught. So this is the k naught and this is less than k naught, so we can write this is 2 k naught, and using the value of gamma as well, so we can arrive at this result that Tn of x, norm of Tn of x will be less than or equal to this. Now when we apply supremum to this, so we will also apply supremum over here, supremum with norm of x equal to 1, then we obtain this thing, And according to the definition, this is, according to the lemma, this is equal to this, and this means that this is now less than or equal to this. We can say that is some, this is because this is some real numbers, so we can say that this is now bounded, and this completes the proof. Thank you.